Hello everyone. In this video clip today, I'm going to cover the very last section of our course, Calculus 1, Section 5.5. This is also, in my opinion, this is the most important section for our course. It is about substitution techniques. Basically, you're going to learn these techniques to solve for classical integration problem. And I grant that if you master the substitution techniques, you're going to be able to solve a large portion of classical problem in integration. So basically what it is about trying to simplify your integral, make it look simpler from a more complicated integral. You try to simplify it, make it look simpler, and you can solve for it. So let me start with an example. Okay, how about this? We call the integral means antiderivative. If you got something like f to the 7 dx, what is that equal to? And of course, you don't need any substitution yet. I start with something extremely easy. In other words, you're looking for the antiderivative of x to the 7. And you know there's going to be 1 over 8 x to the 8 plus c, because the derivative of x to the 8 is 8 times x to the 7. 8 going to cancel 1 over 8, so you have the answer, right? Because I have a simple function in here. In other words, you hear what I'm saying. Small f of x equal to x to the 7. Then big F of x is equal to 1 over 8 x to the 8 plus c. That's all I'm talking about. Derivative of big F is equal to the function small f. That's all. This is the antiderivative of this function. Okay, but life's not that nice to us all the time. What if you have a function that's a little bit more complicated? So you got integral of 2x plus 3 raised to the 7 dx. Oh boy, we don't have just x to the 7 anymore. You have a bigger mess inside. So we somehow kind of wish that thing is simple thing, right? So the substitution technique is going to work this time. What if I let u equal to 2x plus 3? Okay, so the whole thing right here, the mass of the 7 is just u, right? So this is the integral, this is u to the 7. Alright, but in here is dx, integral of x. Now you do a u sub, right? U is big mess, so somehow you gotta write du in here. So what is du in terms of dx? Converted, right? So differentiated, this means what? Du over dx is equal to 2, right? Is that right? Another word, du is 2 times dx. I just multiply dx on both sides. So yeah, difference. I am using Leibniz notation in here. This is no more than u prime. This is du over dx equal to 2. Or du equal to 2 times dx. And here dx, so divide both sides by 2. I got what? 1/2 du is equal to dx. You see what I'm trying to do in here? I try to rewrite everything in terms of u. So 2x plus 3 is my u. So 2x plus 3 to the 7 is u to the 7. And what is dx? Dx is 1/2 of du times 1/2 du. 1/2 is a constant. We can pull it outside. 1/2 integral of u to the 7 du. Now you have a very simple integral. Instead of a big mess to the 7 dx, now what? Just u to the 7 du. What do I know about u to the 7 du? I don't say in here everything is just a dummy variable. So u to the 7 du is 1 over 8 u to the 8. Oh, I say u to the 8, right? Plus c. But don't forget that you got 1/2 in front, so 1/2 times 1/8 u to the 8 plus c. And again, u is not our variable, it's just u is our substitution. We have to bring it back to x, so simplify this a little, it's 1 over 16. U to the 8 is 2x plus 3 to the 8, and then plus c. That will be our answer. And I grant that if you differentiate, you take the derivative of this big F right here, you're going to come back to 2x plus 3 all the way to the 7. Okay? And there are many type of functions you may have, so it depends on the type of function you choose different sub. And this is very normal if you choose a wrong sub for the first time. So what do? Just come back and try another substitution. Hopefully that sub will simplify. And how do we know the right sub? Practice. You get there quicker. Okay, give you another example. I give you polynomial already, right? How about exponential function? integral of e to the x dx. Oh, you know that this is just e to the x plus c, right? What if I have this integral of e to the 5x plus 1? See, my exponent is not symbol anymore, dx. Okay, so this one is not a single x, so you don't have the answer symbol right here anymore. We're going to do a u sub. That u equal to 5x plus 1. And then du over dx is equal to 5. If I plan on later on, you guys are not going to write this way anymore. You're going to move directly to the next step, which is du equal to 5 dx. Then you can skip this one. You write all the way to here right away. What did I get from here to here? I multiply both sides by dx. I have this. And then I have to convert everything to u. So dx is 1/5 du. So this problem becomes what? Integral. Okay. E 5x plus 1 now is u. And what is dx? 1 over 5 du. Dx is 150. You said I changed the variable entirely from x all the way to u. And of course, I know the 1/5 is constant. I can bring it outside. Integral of e to the u du. And you know that e to the u integral is just e to the u. So 1/5 e to the u plus c, which is 1/5 e to the what? 5x plus 1 and then plus c. Okay, let's move on to another example. How about this time? I'm going to keep this example, but I will add the upper bound, lower bound to it. Okay, so what if I have integral e to x dx, say from 1 to 5, and then the answer is going to be what? E to the x, we call it from 1 to 5. We wrote it this way, which is plug in x equal to 5, so e to the 5th minus e to the 1, which is e to the 5th, minus e. Okay? Same thing here. What if I have, instead of e to the x, I got e to the 5x plus 1, so you run from 1 to 5. Alright? So the idea is pretty similar, but now you have to worry about the boundary, right? Integral from 1 to 5 e to the x, e to the 5x plus 1 dx, and you do the same sub, u equal to 5x plus 1, and you change into u. Now you have to calculate the boundary for u. X run from 1 to 5, and u run from where to where? Plug in, x is equal to 1, right? Then x equal to 1, then u is 5 times 1 plus 1 equal to 6. See, x is 1 right here. 5 times 1, 5 plus 1 is 6. And then the second case, the upper bound when x equal to 5, and u is equal to 5 times 5 plus 1 equal to 26. Another way, when x runs from 1 to 5, and u going to run from 6 to 26. So make sure that you change the boundary. This is from 6 to 26. Okay? X is 1, the whole thing is 6. X is 5, the whole thing is 26. Okay, so e to the u, same thing, but now the boundary is 6 to 26. Here, 6 to 26. So instead of plus c in here, e to the u run from 6 to 26, which is 1/5 e to the 26 minus 1/5 of e to the 6. And you have the answer. So very similar. Just make sure that you do some extra work in here, calculate the boundary, make sure that you convert the boundary from x to u as well. Not the same boundary, okay? The boundary is going to change. Let's try more examples, okay? How about some tricks up? So you have to know some derivative for trig to play around with trig sub. You know the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of tangent is secant square, the derivative of secant is secant tangent, okay, etc. Some of them, and even invert trig. Look it up if you don't remember. Let's try some. So I'm going to give you an example. How about integral of sine x times cosine x dx. So what do I have in here? Sin x times cosine x, okay? dx. And how do we sub in here? You know that the derivative sine is cosine, right? Or the derivative cosine is sine. So if I let u equal to sine x, then du over dx is cosine x. The derivative of sine is cosine. And again, later on, you don't write this line anymore. You're going to write right away. So it's what? Du is equal to cosine x dx. Okay, I'll multiply both sides by dx. So u equal to sine x, du is cosine x dx. You can skip the middle line right here. Right here, save some time. Okay, so this is du, cosine x dx. This is going to be your du. And sine x right here is going to be your u. This problem becomes integral of u du. Okay, from the problem that looks longer, look more complicated, if simplified with a simple sum, this integral becomes much simpler. Integral of u is what? 1/2 of u squared plus c. Right? And this is 1/2 of sine squared x plus c, because your u is sine x. So far, so good. One more. Just try to give you as many examples as possible I can think of. Okay. How about this? Integral of tangent x dx. It looks simple, but well, it's not that easy. So tangents, you may think of derivative tangent or secant. I try not to bring new trig function in here. Usually, I try to bring it back to sine, cosine. Take my advice on that. Okay, it may not work 100% of the time, all the time, but many times, most of the time. Integral of tangent is what? Sine x over cosine x dx. Because tangent is sine over cosine. You see why sine and cosine function are better? It's because the derivative sine is cosine, the derivative cosine is negative sine. So it's just playing around with those two. Okay, so I have sine and cosine. So what I see in here is sine x dx on top. Right? So I'm going to let u equal to cosine x. Why is that? Because if I do that, then du is going to be negative sine x dx. Right? Derivative cosine is negative. So sine x dx is negative du. Well, this becomes integral right here. Sine x dx is negative du, and cosine x is u. Well, this is no more than negative outside, 1 over u du, right? It's negative, it's constant, -1. It's constant, I'll bring it outside, and this is 1 over u du. And you recognize this integral right away. This is ln of u, right? With a minus outside, absolute value of u, and then plus c. This is negative ln of cosine x, and then plus c, because u is cosine. So you have the answer. Okay? So I think it's on this section 5.5, we assume that this is the first time you guys see the substitution technique. So what I see is the homework exercise is a kind of simple, not too complicated yet. Just need to spend some time in practice. Let me give you about 2 more before I stop the video. How about make something a little bit more complicated? How about this? Integral of x times 3x squared plus 7 raised to the 14 dx. You see what we have in here? X, right? And then the integral of big mass raised to exponent and then dx. Okay? So just try it. Usually my experience is whenever I see something complicated, I'll do the u sub for that thing. If I let u equal to 3x squared plus 7, I do that u sub, then I have to differentiate because I have to convert a dx. So du is equal to, now I skip the intermediate step, okay? 6x dx. See? first time, so let me just write the whole thing, make sure everyone get it. du over dx is 6x, derivative. 3 here, bring the 2 down, comes 6x. So du multiply both sides by dx, du is 6x times dx. Okay, so I have what? X here, dx there, right? So x times dx is 1 over 6, du is x dx. So this problem is integral. The one from here to here is u to the 14, and then x dx is 1 over 6 du. So 1 over 6 the constant, I'll bring it outside, and then du. And see, from a big complicated problem becomes something simpler. 1 over 6, 1 over 15, u to the 15 du. Integrate u to the 14 is that, so what? 1 over 90, u to the 15 is 3x squared plus 7. Don't forget the no. I'm sorry, it says no du in here. Plus c, I mean. So 15 and then plus c. All right. And that would help. And then one more thing that I'm not going to give you an example on this, but because I want you to try it by yourself. I'm just saying this. Many problems you may have more than one way to do substitution. It means what? Some people do sub this way, some other may do another use of a different substitution, and like both ways will work. Both ways may work. So just try, just practice. You may see that one way may work faster than the other way, but I never say that the substitution will be unique. Okay, and I'll let you practice on that, and you see. You can try. Okay, one more example, then I will call it the end of the section. I see this in the book, so let me do it. Okay, let's see. Integral of secant square of x over tangent square of x dx. So what do I see here? I see trig function, trig integral. I got secant and tangent involving, and I know that what the derivative of tangent is secant square. So, and I see in here we have secant square right away. So obviously my sum is u equal to tangent x, because with that something du is equal to secant square of x dx. So this part right here will be my du. So this problem becomes integral is du on top, right? This is du, and over tangent square is u squared. So this is the same thing as integral of u to the -2 du, because 1 over u squared is u to the -2. Now I can use the power rule one more time. This is add 1 to it, it's going to be -1, so negative u to the -1 plus c. I'm using the power rule right here. The number go down reciprocal. Add 1, -1, reciprocal -1 is -1, and use the -1, okay? Which is negative of u is tangent, so 1 over tangent x, and then plus c. That'll be your answer. See? As I mentioned before, there's no way for me to cover every single problem on the substitution techniques. There's a lot more problems you want to see later on in your homework and your quiz and your exam. You practice more later on, especially when you guys move on to Calculus 2. You guys are going to see more complicated problems using the substitution technique. But hopefully, via a couple examples in this section, you guys see the main idea of it. Right? Try to simplify a big, complicated integral. Bring it down to much simpler, the one that you know. And then you can integrate. That was the main point. And how to choose the right sum? Well, depends on the nature of the problem and depends on your experience. Then we choose a good, correct substitution right away. Just practice, and you guys are gonna get through it. Okay. I'm gonna stop the video clip right here. Thank you for watching, everyone. I hope those examples will help you to learn a little bit more. And as usual, please don't hesitate to ask if you have any question. Thank you for watching.